Now in this section, we want to be looking at the chain rules for functions of several variables. Now here in this excerpt from the Calculus 1 textbook, you can see the definition of the chain rule. Let me just show you how some of the interpretation for this goes. If we have y as a function of u and u as a function of t, then we can find the derivative of y with respect to t according to this by doing the derivative of y with respect to u and multiplying by the derivative of u with respect to t. Now, of course, since we're doing the derivative with respect to t, we would like our answer to come out all in t's. So we will change the u back into sine 5t. So here's what it looks like with functions of several variables. Here we have z as a function of x and y, and we're going to use x and y both as functions of t's and see how do we find the derivative of z with respect to t. Now, there's a nice way of remembering the pattern of what you do by drawing a tree diagram. If we start with z, which is a function of x and y, and then x is a function of t, and y is a function of t, this is the tree diagram. On each of the branches, for example here, we could do the derivative of z with respect to x, so we'll put that on the branch between the z and the x. The derivative of x with respect to t is on the branch between the x and the t. So we draw off our tree diagram and label it appropriately. Now, if we want to do the derivative of z with respect to t, we can get from the z to the t by going from the z to the x, and then from the x to the t. We could also go from z to y, and then from y to t. So these are the two branches where we can get from z to t going through the derivatives. So we multiply along the branches and then add down the end. So that's our formula, if you will, for this particular chain rule. Now here's how that would play out doing this derivative. So we've got the derivative of z with respect to x. We've got the derivative of z with respect to y. We've got the derivative of x with respect to t, and the derivative of y with respect to t. We put those together in the pattern that we just wrote, and again, we want everything in terms of t's. So we need to take the x's that we have and replace them with sine 2t. We need to take the y's and replace them with cosine t. So that's our derivative. Now here is a slightly different problem. So we'll have a slightly different looking chain rule. look for the patterns and the ideas behind the chain rule. We're trying to find the partial of W with respect to S. So we have Z as a function of X and Y, and X is a function of S and T. Y is a function of S and T. So here's our tree diagram for this. Now again, we will put on each of the branches the appropriate derivatives. And if we want to do the derivative of Z with respect to S, we need all of the branches that start with Z and end with S. That would be these two. We multiply along the branches and add down the outside. Now, likewise, if we wanted the derivative of Z with respect to T, we need to find the branches where we can get from Z to T. Now, we already know which ones we need to be putting together from our tree diagram that we just did. So let's do the legwork for the partial of W with respect to S. We need the partial of W with respect to X, the partial of W with respect to Y, we need the partial of X with respect to S, and the partial of Y with respect to S. We put those together in the pattern that we just wrote down from our tree diagram. And substitute for all the x's, st squareds, and for all the y's, s squared t's. Now there are a lot of different versions of this chain rule. Here we have u as a function of x, y, and z, and we're going to have x, y, and z as functions of s and t. So if we had to do a partial of u with respect to t, one option is to construct the appropriate tree diagram. However, I'm going to show you what the pattern looks like. Now this is the definition from our textbook for the chain rule. It's not very informative. You can look it over if you like. Notice how it's talking about the I as being however far you need to go. So let me show you the idea behind doing the chain rule without a tree diagram. So here we're trying to find our derivative of u with respect to t. Well, we can do the derivative of u with respect to x. We can do the derivative of u with respect to y. We can do the derivative of u with respect to z. So let's do all of those. We can also do the derivative of x with respect to s, and the derivative of x with respect to t, and same thing with y's and z's. Now we don't care anything about the s's, so we don't worry about the derivatives with respect to s. However, we can do the derivative of x with respect to t, derivative of y with respect to t, and the derivative of z with respect to t. Now, if you've caught on to what you've been seeing on the tree diagrams, you notice here we've got a derivative of u on top and a derivative of x on bottom. Here we've got a derivative of x on top and a derivative of t on bottom. If you take the derivative of u and the derivative of x and the derivative of x and the derivative of t, you can think about those as canceling, since one's on top and one's on bottom, and you got the derivative of u with respect to t. Now that's only from the first two. Notice we can do something similar for these two. If we take the derivative of u with respect to y and multiply by the derivative of y with respect to t, then we get the derivative of u with respect to t. If we multiply these two together, then we get the derivative of u with respect to t. So look, we got the derivative of u with respect to t three different ways. We need to combine those together. So that's our chain rule without any tree diagrams. We change the x's, y's, and z's back into s's and t's, and there's our answer. Alright, so let's try this without the tree diagram. We're trying to get from u and s. We can go u and x, so the partial of u with respect to x. We can go from u to y, that would be the partial of u with respect to y. And we can go from u to z, that would be the partial of u with respect to z. So let's find these. The partial with respect to x, in the first term here, that would be a 4x cubed y. That would be a 0, since there's no x in it. The partial of u with respect to y would be an x to the 4 and a 2yz cubed. And the partial of u with respect to z would be 0 and 3y squared z squared. Then we can get from x to s. I'm not going to draw arrows to all the other ones because we only care about getting to the s. So we can go from x to s. The derivative of x with respect to s would be re to the t. The derivative of y with respect to s would be 2 rs e to the negative t. And the derivative of z with respect to s would be r squared sine t. Okay, so again, the partial of u with respect to x times the partial of x with respect to s is like the two x's canceling, and we get u and s. So this would come out to be, I'm just going to write it all out, partial of u with respect to s would come out to be a 4x cubed y times an re to the t plus an x to the 4 plus 2yz cubed times 2rs e, I don't know what that's supposed to be, but it's not supposed to be a negative 2, negative t, plus 3y squared z squared times r squared sine t. So there's our rule without any tree diagrams. Now the last step, of course, is change the x's, y's, and z's into r's, s's, and t's. And so that would come out looking like this. And of course that would simplify a pretty good bit, which I'm not going to take the time to do that. Now here's a problem from Calculus 1 that I wanted to remind you about: implicit differentiation. And remember, to do implicit differentiation, and where we can't solve for y as a function of x, we simply did the derivative of each term and then solved for the y prime. And we're going to change this up a little bit and talk about a little formula we can use for doing implicit derivatives in functions of several variables. So all I've done on this one is to move the 2lny over to the left so that we got everything equal to 0. Now that's the key to the formula working out the way it works out. Now we're going to call this capital F, function of x and y, and we've got capital F equals 0. So if we do the derivative with respect to x, this is what we get. The partial of f with respect to x times the change in x with respect to x, plus the partial of f with respect to y times the change in y with respect to x, and the derivative of 0 is 0. Simplifying and solving for dy dx, we get this. Now this is kind of our little magic formula that we're after. Look at this. We've got dy over dx, and what do we have here? Partial with respect to x, partial with respect to y. Notice that they are just in opposite positions. Notice also that there's a negative sign on it. So if we have this formula for dy dx, look, all we've got to do is use a little imagination, and you can reverse the calculations that I just did and come up with this. If we wanted to do dx dy, look again. Here's the partial with respect to x. Here's the partial with respect to y. And we have a negative sign on it. And finally, what if we had a function of x, y, and z, or any number of variables? Do you see the pattern? If we want the derivative of z with respect to x, we do the partial with respect to x on top, partial with respect to z on bottom, and give it a negative sign. Same pattern. Partial of z, partial of y, negative sign.